Hey kiddos, so today we're going to take all the vocab that you learned on whatever day that was, and we're going to apply it to a problem. And here's the function we're going to apply it to, and we're going to go find relative max and relative min and intervals of increasing and decreasing and intervals of concave up and concave down. Just going to kind of run through everything. So hopefully this is a vocab review for you and an algebra review for you. So first we need a derivative, and I wrote a really boring, really nice polynomial. I know it looks terrible, but watch what happens when you start taking derivatives. So I'm going to pull the 3, cancels the 3, and subtract 1. Pull the 2, cancels the 2, subtract 1. Oops, I said cancels the 2 and I didn't do it. And then here. So there's your first derivative. Now we got to go find critical points. And remember that a critical point is where your first derivative equals 0 or doesn't exist. Well, this is just a pretty little quadratic, so it's going to exist everywhere. I don't have to worry about the not existing. But it equals 0, and I'm going to have to go factor to find that. Remember factoring? It's back. It's so fun. So I'm finding that this equals 0 at -1 and +2. All right, so what does that mean? We're going to do what's called a number line analysis. I'm going to put these on our number line, and we're going to go analyze our derivative. And what we're analyzing is the derivative. But I'm going to use this version of it because all I care about is the value positive or is it negative? Because I need to know what intervals my function is increasing and decreasing on so that I can write them in interval notation. So if I'm going to use, I'll write it up here so it's right in front of my face. I'm going to use this version. I'm almost always going to use the factored form if it factors because it makes this easier. So if I pick a number to the left of -1, like -8 billion, and I put it into x, -8 billion minus 2 is still negative. -8 billion plus 1 is still negative. A negative times a negative makes a positive. Okay, between -1 and 2, I'm probably going to pick 0 because that's the easiest. That will give me a negative here, a positive here. A negative times a positive is negative. And a number bigger than 2, like 75, is going to give me a positive times a positive, keeps it positive. So what that means, I plugged into my first derivative, remember? So these are first derivative signs. The first derivative is positive and the negative and then positive. And now I know things about our original function. If your first derivative is positive, remember your vocab means your function is increasing. First derivative negative is decreasing and then back to increasing. So, you know, I haven't asked you a question. Nobody's asked a question. But if they weren't to say, find the intervals over which function is increasing, this is how you would do it. And this is how you would lay it out. This doesn't count as showing your work. This is like scrap work off to the side that you would do. So let's write one out properly. You would say f is increasing where f prime is greater than 0. So you're giving the definition of the thing they're asking you for. And then you're going to say, I'll use interval notation. So this would be negative infinity until -1, open, and then picks back up again at 2 and goes forever. And those are open interval. They're not closed. You can't be increasing at a turning point. So that could be a question that they ask. Another question that they ask that we've just done all the work for, they could say, find the local minimum. So local minimum. So you would write that by saying f has a local min when f prime changes. So local min is when you change from decrease to increase, so down to up. So it's when f prime changes from negative to positive. Negative to positive. And we would say that that is at, let's see, we change from increase to negative to positive, decrease to increase at x equals 2. So they could ask either of those. They could have even just asked for critical points, and then we would have been done way back here. So these are our critical points. Those are the ones I put on my number line, and then I'm doing number line analysis to decide increasing, decreasing. When I know increasing and decreasing regions, then I know relative maxes and mins. And that's everything you know about from a first derivative. So let's do a second. So same function. We're just going to do the same thing. I got to scroll so I can see it. If I take a second derivative, I'm going to get 2x minus 1. So this is going to have, I'm going to go look to see where it equals 0. And that's going to be at x equals 1/2. And if you remember, that's called a hypercritical point. And that's the number I'm going to use on a number line again. So 1/2. This time, when I go analyze my second derivative values, function values, and I pick a number that's less than 1/2, like 0, I get a negative here. And then I pick a number that's bigger than 1/2, like 82, I get a positive here. Then when I say what that means about f, this is determining concavity. So a negative second derivative means that we are concave up. Oh, nope, down. Down. And this would be concave up. That's it. They could come over here. They could ask you for a point of inflection. And we'd say we have a point of inflection when f double prime changes sign. Because I know my vocabulary, so I just am writing the vocab down and I'm writing the definition so that the person who's reading knows that I know what I'm doing. Or they could say, find the interval where it's concave up, and we would say f is concave up. Notice that I don't write CC, I have to write concave when f double is greater than 0, and that happens over the region from 1/2 and on. Or you could say x is greater than 1/2. You can use interval notation or inequality notation. The end. So not a lot of complicated calculus here. It's all vocab. I tried to tell you, everything is vocabulary. There's a little bit of algebra coming at you. You got to make sure you know how to factor. But typically with these problems, the derivatives are not really challenging, like the taking of the derivatives. Be on the lookout for a product rule or quotient rule here or there. But they're not going to give you something really, really complex, because then you have to go like solve it, like set it equal to 0 and solve. So they can't give you something terrible and not give you a calculator, but that's coming soon. All right, kids, let me know if you need anything.